Okay, time is 2:30, so let's begin here. So since we last met, all of you should have received your project number 4s back. Again, the grades were good. Were there by chance any questions? Okay, so project number 5, hopefully all of you brought that with you. We will discuss that very shortly, and that is due on April 17th at noon. Test number 2 is 1 week from today. We will spend the last about half hour of class reviewing for that. And again, corresponding to what I mentioned in my listserv posting over spring break, there will be no class on Thursday. Are there any questions before we get going here? Okay, let's begin by talking about project number 5. So there are 3 problems with project number 5. It's essentially the same format as we've done before. You can work in groups as you wish. So problem number 1 deals with the Lystra data again. I'm sure after taking this class, you're probably very interested in what is a Lystra or Lystra, and probably want to actually maybe even try it. But anyway, so what you're going to do with the data now is similar to what we did with the Larry Bird data set in Chapter 4. And that is to analyze the data in a log linear model format. And so if you take a look at the Larry Bird data set, how we approached it in class, this problem is going to be fairly straightforward. Problem number 2, when I wrote this up, it was shortly after Leonard Nimoy died. And so this kind of inspired me to include this particular problem here. So I think probably most of you have seen Star Trek, the original version of Star Trek. By chance, any Star Trek fans here? All right, good. It's always interesting. For some reason, every once in a while I have a reason to ask that, and no one wants to admit. So those of you who raise your hands, you got the courage to say, yes, I'm a Star Trek fan. On a little bit of a side note, I just recently, about a week or so ago, came across, I guess there are like fan series for Star Trek, and I came across Star Trek Continues. And basically they have the exact same characters as the original series, but of course different people playing them. And it is, I would say, at least 95% as good as the original series in terms of the storyline and also the just the like the studio scenes. I mean, it looks like they're actually on the Enterprise. So Google Star Trek Continues. And there are 3 episodes out there, and the 4th one's coming out in May. And you probably never expected to hear that in a stat class. So I think all of you realize that in Star Trek, the crew members tend to wear different colored shirts that correspond to what their jobs are. So here's members of the original series there. So you see Captain Kirk here in his gold uniform because he's the commander, and various people who drive the ship, let's say, or helmsmen, are also in gold. Now, if you're a science officer or medical officer on the Enterprise, such as McCoy and Spock, you got blue on. And then lastly, if you're security or engineering operations, you got red on. Okay? Now, in future, or in, I shouldn't say necessarily future, but in subsequent Star Trek series, they actually changed the coloring a little bit, but that's not important here. We're just going with this coloring on the original series. And somebody who perhaps had too much time on their hands watched every episode and counted the number of casualties associated with the different colors of shirts that people wore. And if you're a Star Trek fan, you know that you want to, well, typically it's thought of, you want to avoid wearing a red shirt. If for some reason you're actually on the Enterprise, you want to avoid wearing the red shirt because at least our perception is, as a Star Trek fan, is that those are typically the people who died the most on the show. Very many times Kirk will go on an away mission, they have this random red shirt guy who comes along on the away mission, and that person gets killed. So anyway, so there was a interesting analysis that was done in a stat magazine about, well, it doesn't really matter what color shirt you wear on Star Trek. And I'm actually going to approach this, or you're going to approach it in this project in a little bit of a different manner than what they do there, but you're essentially trying to do the same kind, answer the same kinds of questions, and that is, it doesn't matter what color shirt you have. So what I did here was I created a data frame called Trek, for the lack of a better name, and there's the corresponding data in terms of the casualties, and also I don't really necessarily, maybe I'm not a big enough Star Trek fan to know this, but I guess there are resources available where you can figure out, well, what's the crew complement by the by what a member of the crew does, and you can correspond that to the shirt color. So, for example, 136 individuals on the Enterprise wear a blue shirt. And so, so you might be thinking, okay, well, 7 out of 136 died. Well, that's not quite correct, because while people die on the series, you know, the Enterprise then can get crew replacements. So this isn't just this is not a binomial problem. Rather, it's a Poisson problem, where the Poisson response is casualties, and then the crew there, that represents what we've been calling T. You know, similar to how we had, let's say, the number of melanoma cases in Omaha versus New York City. You know, the population size of that city was our T. And we're going to adjust for it by using an offset in our model. Okay? Any questions about the data? Okay, so problem A. Why can't one simply conclude that the red uniform crew members were more likely to be a casualty because they have a larger number of casualties in the data set? Obviously, 24 casualties there, which is the tops of all the different colors. Why can't one just conclude, yeah, the red, you know, typically has, you're going to have more casualties. This should be a very easy question to answer. Just think about it for a minute if you don't know what the answer is right now. I think it should be really easy. It gets into the heart of what we're doing with Poisson rate regression models. So part B then says, well, let's estimate a Poisson rate regression model using casualties as the response variable, color of the shirt as the explanatory variable, and crew as our baseline measure, RT. So estimate the model, state the model, of course, and then using a likelihood ratio test, one likelihood ratio test, tell me, does uniform color matter? So do the test, state the p-value, state a formal conclusion. Then we want to examine more in depth the relationships between the different color shirts here. So just using, you could say, the population model itself. So not with any estimates. I want you to derive the ratio of the means for the red and gold shirts. So notice here, shirt is actually a categorical explanatory variable. And we first saw those in chapter 2. And with respect to odds ratios, you know, we say, okay, you got to be careful about how you handle them, and we derived odds ratios associated with it. Well, what I want you to do now in terms of a Poisson regression model, rate regression model, derive the ratio of means. Once you do that, then part E is kind of implementing some of the stuff that you just did in D, where I want you to compute 95% profile likelihood ratio intervals for PC, which stands for, again, that percentage change, which is kind of like the odds ratio that we saw in chapter 2 in terms of the actual numerical format of it. Find the likelihood ratio intervals that compare those shirt colors. And of course, interpret. Then part F actually relies on something in chapter 5. And you will shortly be able to do that. It's not going to be very difficult. So that's problem number 2. Problem number 3 then is like a problem that I've given you in the past, where more so it was with odds ratios. Here you're now working with the percentage change. And so let's say we have a particular Poisson regression model that has 2 explanatory variables in it, x1 and x2, but also notice there's an x1 squared. What I would like you to do is, well, derive the PC, the percent change in the mean response for C unit change in X1. Come up with a formal interpretation of it, and then tell me what the Wald interval would be for that corresponding expression. Okay? So, that's project number 3. Are there any questions? Now, obviously, this project is not due before the corresponding test that we have coming up here, but you should at least look at this project before the test, because there could be some very similar problems. You know, again, there's only one part that is from Chapter 5, and Chapter 5 is actually not on our exam. Any questions? Okay, good. Let me close out some files here, and we'll get back to the notes. Okay, we left off about page 5.2, 5.3 in the notes. What we were talking about was ways that we can determine what explanatory variables should be in our model. And the primary tool that we're going to use for that is something called an information criteria. And this information criteria is based upon your log likelihood function, evaluated at the parameter estimates. And also included in it is a penalty for having too many variables essentially in your model. Maybe variables or terms that are not needed. And what we said last time was that the smaller the information criteria is, the better the model. So you can almost say the best model overall is the one that has the smallest information criteria. Now there's actually 3 different information criteria that are typically used. One is not necessarily better than the other, so that's why there's 3 rather than the best one. And all of them differ based upon what they use for this penalty, which I call K. And so Kake's information criteria uses 2 as K in the information criteria equation. The corrected AIC uses something that's based upon the number of, the sample size n, and also the number of parameters in your model, which I just generally call R. Now notice in this expression here, for the corrected AIC, you can actually rewrite it so it's the AIC plus something else. So what's going to happen as your sample size increases and you keep your number of variables in your model fixed? What happens to the corrected AIC? It becomes approximately equal to the AIC itself. So note that for large sample sizes, the corrected AIC is going to essentially give you the same results as the regular AIC. And you can also kind of see that too by taking a look at it as an expression of the information criteria. So the penalty is 2 times n divided by n minus r minus 1. Again, look what happens as n increases. Essentially it goes to 2, which is what AIC is. And then lastly, the Bayesian information criteria uses the log of the sample size for its penalty. Now note that log of n will always be greater than 2 when n is greater than 8. So as long as you don't have an extremely small sample size, the BIC, the Bayesian information criteria, is always going to use a larger penalty. So what's the end effect, though, of using a larger penalty in comparison to the AIC? So again, the smaller an information criteria is, the better the model. Take a look at the expression. Where does the penalty come in? So the penalty is K. R is the number of parameters. So, what's going to happen with the BIC in comparison to the AIC? Is the answer there? It might be. It kind of is there.
You know, be more likely to say that parameter should not be included.
Perhaps. I think you're kind of getting at it. So, you know, look at K times R. So as the number of parameters increases, what's the effect of having a larger penalty? Is it going to make the information criteria higher or lower for BIC versus AIC? Higher. Because a K is a larger penalty. So which do you think favors the smaller models, meaning the models with less parameters, BIC or AIC?
Yes.
No, BIC. The BIC favors smaller models because, again, it has a larger penalty. So as the number of parameters increases, that penalty is going to be coming more and more and more into play. And again, the smaller the information criteria, the better the model. So that's why the BIC favors smaller models. Now, as I said to you earlier, there's not necessarily one best information criteria. That's why we're looking at 3 different ones here, or 3 most commonly used ones. You know, some people will say, well, the BIC is better because you get a smaller model. Well, yeah, you get a smaller model, but just because it's smaller doesn't mean it's a better model. Okay? I think that's a very important point. Just because a model is smaller doesn't mean it's necessarily better. It's just using this criteria, that's what will happen. A smaller model will be chosen as the best. Obviously, if you have a smaller model, it makes it easier to interpret, right? So you have less parameters you have to worry about, less explanatory variables in your model. But it doesn't necessarily mean it's a better model.
So what do you mean by smaller model?
Less explanatory variables. Okay? If you have less explanatory variables, you have less parameters. Now, how can you calculate these? Well, there's a nice little function called AIC that will allow you to do it. And you can specify essentially the model that you have just estimated as an argument in there, and also what you want for K. And this will be coming very handy then for problem. Oh, why can't I find it fast? Problem 2F in the project. Okay, so the smaller the information criteria, the better the model with respect to these criteria. So what models do you look at? That's an important question. So, you know, I've given you a tool to decide which model is better. But we haven't talked about, well, which models do you look at? And so one approach will be to do what's called all subsets regression, where what you are kind of doing, and notice I have this in quotations, is you're looking at all possible models that one could have. But notice that's in quotations. So let's say I have capital P total variables. That means then I would have 2 to the P different possible models based upon the main effects. So, you know, obviously if I have 3 variables, 2 to the 3 is 8. But look at what happens if I had 10 variables. 2 to the 10 is 1,024 different models. And you can keep on going higher and higher and higher. You can see that the number of models that you would have to investigate could be quite substantial. So with respect to p equal 3, just to make sure you understand this, what would be all the possible models? Well, you could look at a model that has no explanatory variables at all. It's not much fun, but that is a possible model. And then one that has maybe just x1, one that maybe just has x2, or maybe one that has x2 and x3, or one that has x1, x2, and x3. So the name all possible subsets comes from the fact that you're looking at all possible subsets of these variables put into a model. What you could do is estimate all eight of these models, calculate your information criteria. The model with the smallest information criteria is the best according to that criteria. That's simply how it works. But as I said here, this 2 to the p can actually become large quickly. So what can you do? Instead of looking at all possible models, maybe what you could do is use a mathematical algorithm that allows you to maybe look at just some of the models, but still have a certain level of, I'm going to use this word, but probably not in the best context, a certain level of confidence that, yeah, you've looked at enough that you can conclude this model definitely has the smallest information criteria of all the models. And there are a number of mathematical algorithms that can be used. We're going to talk about, just kind of in a big picture sense, one called the genetic algorithm. The name genetic comes from the fact that of how this algorithm works in terms of genetics, or has some genetics analogies, I should say. So this is how the algorithm works. Random sets of explanatory variables are put together into models. So maybe let's put x1 and x2 together. Maybe also let's put just x3 by itself in a model. Then this is called the first generation of models. From the best performing of these models, meaning maybe the ones that had the smallest information criteria values, new models are formed. So maybe x1 and x2, that model, was really good, and also the model that just had x3 was very good. Well, what this algorithm does for a second generation of models is, well, why don't we put those variables together into one model? Because if these were good by themselves, maybe they'd be good together. So the second generation is formed in that manner. And again, you look at, well, what were the best of these models that you just formed in the second generation? This whole process continues for multiple generations, where also there's a component of random additions to a model, in terms of, well, maybe I'll randomly add, without necessary justification, maybe I'll randomly add x4 to my model for some reason, if there wasn't a fourth variable. And also random deletions as well, which are often referred to as mutations. Again, the genetic analogy there. To try to see, can one come up with a better model? And this process continues, and continues for multiple generations until eventually the algorithm reaches convergence, meaning no matter how it mutates or whatever new models are formed, it just cannot find anything better. And so then the algorithm ends. And that's how it works. Now, this algorithm does not necessarily, again, look at all possible models that could occur. Instead, what it does, it looks at subsets. And based upon how the algorithm works, it's hoping that eventually at some point it's going to get to the best overall model by not necessarily looking at all possible models. But do note that there is actually a stochastic nature to this algorithm, meaning I told you there was some randomness to it. Random variables are added to a model or deleted from a model. And so because of that, as you might expect, when you run the algorithm one time, you might not get exactly the same answer the next time you run it. So because of that, you should try to use this genetic algorithm multiple times to see, hey, do I get any improvement? You'll see what we do in an example shortly. Okay, notice the word not there. Let's go back to this all possible subsets, where we are supposedly finding all possible models. Note that we're actually not really looking at all possible models. All we were actually doing was looking at the first order terms, you could say, or the main effects. Either x1 is or isn't in the model. Either x2 is or isn't in the model. That's what we're looking at. We're not doing anything with interactions. We're not doing anything with any kind of transformation. So because of that, you have to be very careful about really interpreting what all possible means. You know, in the context so far how I've introduced it, it's just in terms of the main effects. You know, there could be some other model out there that's better that includes an interaction term, or x1 squared. But still, we need to start somewhere. And by doing all possible regression subsets, or doing then the genetic algorithm, it gives you a place to start to try to figure out what variables should be in the model, and which maybe don't need to be in the model. So the function that we're going to use to do this is called GL-multi, and it's in the GL-multi package. There are actually other packages that do some of this stuff too, but this is the one when we were writing the book we found was the best. One of the nice aspects of it is it can actually automatically include interactions too. Pairwise interactions, that is. So what that means then is it could look at, in terms of the genetic algorithm, or just all possible models, it will look at, in terms of all possible, it will look at 2 to the p plus a, where a is essentially p choose 2, possible models. So that could be, this is now main effects and pairwise interactions. You can see how this number just is really, really getting big fast. Okay, so let's take a look at an example. We're going to go back to using the Placekicking data set again. Excuse me. So in this data set, there are, let's see now, 1, 2, 3, 4, 5, 6, 7, 8 variables, 8 explanatory variables. And there's 1 response variable. So in terms of the main effect terms, how many possible models are there? 2 to the 8, which is 256, I believe. So if we want to find the best model using information criteria, we have to look at all those models. We have to estimate them all. And here's how you can use then this package and function. So this is a package you're going to have to download first and install. So I'm going to say library GL-multi. And there's a variety of different ways to use the function itself. This is the way I'm going to use it. I'm going to create an object called search.1.aicc. I'm going to specify GL-multi. The Y argument allows me to specify essentially what variables am I interested in. Well, I'm interested in using good as my response, tilde, and I could simply write out all 8 explanatory variables, separate them by plus signs. A quicker alternative is just simply use a period there. What that tells R is that use all the other variables in your data set. So just a quick way to do it. That comes in handy in this kind of a situation. My data is in Placekick, fit function. Well, to estimate a logistic regression model like what we've done in the past with the Placekicking data set, we use the GLM. So note that this is nice that this this actual function here, GL-multi, can actually be used with other model fitting functions too, not just GLM. Level equal 1 corresponds to I just want the main effects. Method equals H means exhaustive. So the H of exhaustive, meaning all possible, so all 256 models. The criteria that I'm going to use to evaluate the models is the corrected AIC. I could have used one of the other ones. I just, for demonstration purposes, decided to use the corrected AIC, denoted by AICC. And then lastly, the family argument in GLM, I have to put that there to say what kind of model I want with GLM, binomial link equal logit. Okay, so this is what happens. So it's going to take a few seconds. And we see a summary after every 50 models that are estimated. And it tells you which one's the best so far. So the crit there corresponds to then the corrected AIC. And eventually, after 250 models, we get down to there. Remember, there's 256 models in total. But this only shows after every 50 in terms of what's automatically printed to your screen. At least after 250 models, this one was the best. The 1 here corresponds to an intercept, then distance, change, PAT, and wind. To see a summary of, well, what was the best model, or models overall, I can use the print function. And what we see here, so it says from 100 models, that means from the top 100 models, in terms of these 256 models, the 100 models with the smallest corrected AIC, the smallest of all those AICCs, 766.73, and this was the actual model right here. There's some other information displayed there. We'll talk about that later in Chapter 5. For now, you don't need to worry about what does evidence weight mean, for example. Another way to summarize all the models then is to use the weightable function. The term weightable will make more sense, again, a little bit later in Chapter 5, so just hold off on why we're using something called that. So if I say weightable, then where I store the results from GL multi and do a head with it, I get the 6 best models in terms of the corrected AIC. And so again, we see distance, change, PAT, and wind, and the smallest corrected AIC. So what would I do with this model now in practice? You'll see this more in section 5.4. I will look to see, okay, now that I've found this, maybe I should start looking at interactions or transformations, or look at, well, are there any problems with the fit of the model? Maybe there's like an outlier. And that's what we'll talk about as we go along in Chapter 5, where in section 5.4, we'll basically kind of go from the start to the end of model, what's often referred to as model building, with this data set. Okay. Let's see. So the level argument, remember I said level equal 1? That again corresponds to just using the main effects. If I said level equal 2, it would actually look at the main effects and their corresponding interactions as well. The method argument for H, again, was it for exhaustive. If I would have put instead G, that tells R to do the genetic algorithm. And so to illustrate what would happen if I use a genetic algorithm with also all pairwise interactions too, let's look at the following code. Note that there are choose 36 different possible models to look at in this situation. So note that this would not be practical to use, an exhaustive search. So that's why I'm using a genetic algorithm. My code's exactly the same except for level equal 2 here. And let's see, method equal G. And then lastly, marginality equal true. What that tells R is, if you have, let's say, a distance in wind interaction, make sure that the main effects for distance and wind are also in the model. That's generally what we would want to do, similar to what we started talking about in Chapter 2. And so by adding that additional part there, it guarantees that this will happen. So, here we go. Now, instead of summarizing after certain number of models are estimated, now we have a summary after particular generations. So 10 generations, 20 generations. And this will actually take some time on your computer. It might take a couple minutes to finish. And you can see it goes for a long time. It goes up to 630 generations. At that point, no more improvements could be found, meaning lower information criteria value. So the algorithm is said to stop or converged. If I do a print of my results that are saved from GL multi, once you start getting out these interactions, obviously the models become longer, and the way it's printed is not always the cleanest. And so what we actually have here are two different models. Here's one, and here's another that have exactly the same corrected AIC. Again, I can do a head with a weightable function. And so we can see, here's one of the models, and here's the other, and they have exactly the same corrected AIC. So what this is saying is that there are some interactions that look to be important, such as wind and distance, and we've talked about that in chapter 2. But we also have some other ones that, such as wind and field, PAT and distance. That's kind of interesting. Why would we have PAT and distance as interaction? More on that later. Now, note that when I did this code here, note that I set a C number. The reason being, again, is that when you run this, there's some randomness involved. And so I want to be able to reproduce my results. So I ran it with this C number, and then I decided, well, what would happen if I use a different C number? So I reran it. Now for the model that I got, actually I got 3 models that had, or I'm sorry, 4 models that had exactly the same corrected AIC, 765.3552, which is actually higher than what we got before. Then I ran it again with a different C number. I got 763.3304, which is, hold on, which is actually a little bit lower than what we had on page 511. So I might try one or two more times, see what would happen. And then whatever I came up with the lowest would be the best model at this stage of the process. Now I wouldn't just say, okay, I'm done. This is the best model overall. Instead, what I would do is now investigate the model more using section 5.2 material to examine for outliers or influential observations. But this at least gives you a starting point to go with. Okay. So some comments. Please make sure you take a look at the last paragraph of section 5.1.3 in my book. I'm going to focus on this next comment here. Unfortunately, running this function is not as easy as other functions in R. And the reason is because the underlying code that's used in this function is actually written in Java. And so to use this function as package, well, I should say, when this package is installed on your computer, automatically another package will be installed called rjava. Now, if you install those, if you try to run my code, you might actually get an error message. The reason being is this. The version of R that you use in terms of 32-bit or 64-bit has to match the version of Java that's on your computer, 32-bit or 64-bit. Now in RStudio in 10, typically by default, you end up running 64-bit R. How do you know that? Well, when you load up R, I'll just do an example here. When you load up R, you see something like this in the R console, 32-bit. If you do it in RStudio, you're still going to see something. So it's 32-bit, 64-bit. Now, again, in RStudio and 10, unless you've played around with the settings, you're probably running 64-bit R. It's very likely that the version of Java that you have on your computer is 32-bit. So for example, if I were to use Microsoft's Internet Explorer, let's say I just got my computer, use Microsoft Internet Explorer, and I come across a website that says, oh, you need Java. We've all experienced that before, and often with new computers, then what you're going to do is have to go download it. Internet Explorer itself, typically the version that most people will use is 32-bit. So when you go to Sun's website to download Java, it will see, oh, you have a 32-bit browser. I'm going to install 32-bit Java. Well, then that's going to cause problems then when you're running GL multi. Because you have 32-bit Java, and you're probably going to be using 64-bit R. So what can you do? Well, there's nothing stopping you from using 32-bit R. So for example, that's essentially what I'm doing here. So here is my program, and rather than highlighting code and then coming up here to transfer it over to R, the 64-bit that's working with 10, what I do is I just copy and paste into my 32-bit R that I have open separately. And that will be enough to get you by in this class. Obviously, though, it's kind of annoying. And so what can you do? Well, go to Java's website, install 64-bit Java, if you really want to. Now, you may have to reinstall, though, the GL multi package. Just realize that after you do that. Okay. So I'm sorry that occurs. I don't think it's very user-friendly, but that's just the way it is. Are there any questions? Okay, why don't we take some time to review for the exam then? Okay, so of course we'll start at 2:30, but you can go up to 4 o'clock. So just like last time, you can take an extra 15 minutes to finish the exam. The material on the exam is Chapter 2, starting at section 2.2.5, which is page 2.72 of the notes. So everything, I guess the second half of Chapter 2, I guess that's the best way to put it. Chapter 3, and then also Chapter 4. No Chapter 5. There is a formula sheet, of course, with this exam. You can take a look at it. It's on my Graded Materials webpage and my course website. You do not need to print it off and bring it into the exam. You can look at the PDF on your computer during the exam. The test is not finalized, but it's pretty close to being finalized. There's 100 points possible. Problem number 1 is worth 31 points. You're going to be given a data set. You're going to have to use R for some calculations. Problem number 2 is worth 27 points. Data set you'll be given. You can use R for some stuff. And then lastly, problem number 3 is worth 42 points. And it's 5 short answer questions that are not necessarily interconnected in any way. So similar to what was the last problem on the last exam. And there is a 2 points extra credit problem. So that's the layout of the exam. So as I said last time with the exam, I don't think that this test is difficult. There should be no surprises on the exam. But also, you do definitely need to really study. I spent some time talking about that you have to know all the material that was discussed in the lecture notes. If you don't, you're leaving yourself open for the possibility of missing something. So you do need to really study for this exam. Now, with the last exam, I actually gave you a copy of the test that was given the previous year. Notice I'm not doing that this time. But where could you download a copy of a past test that I've given in this class? On my website? Which website? I didn't really realize this until I was writing this exam. I was like, oh, you guys could have done this for the previous exam too. So, hopefully all of you see my books website. In particular, the videos webpage. Right there. I am not going to give you an answer key. This is just the test itself that was given in that case it was for 2012. But I highly recommend that you take a look at it so that you get a general idea of what to expect. Do note that there's, I guess I'm not 100% sure if I did take any questions off that exam or not. You'll find out eventually. So I would make sure that you actually know how to do all the problems on that exam. Do note, though, that that test started with section 2.2.4, so one section prior to what we are starting at, and only went up through section 4.1, I believe. So right before we got to Poisson regression models. So it talked about the stoplight data. That was about where the material ended. So there's some Poisson regression, Poisson rate regression, log linear model stuff that will be on your test that wasn't on that test. Please be aware of that. Just a little side note here. So when I was constructing this website, I did it last summer, and my co-author was taking a look at just checking over for errors and stuff like that, and he said, well, why isn't there a video on some of these dates? And I said to him, well, my students are taking a test. I don't think we need a video of the students taking tests that day. Anyway. Okay, so test structure. The test is structured the same way as before. Excuse me. I'm going to give you a piece of paper that contains the test. You need to write all your answers on it. You use the computer that's at the desk to help you whenever needed to do some kind of calculations in R. Do note that whenever you need to do calculations in R, you still need to somehow show your work on the paper copy of the test. Showing your work could be, let's say, writing out a particular formula that R used to do a particular calculation, Or it could be including some kind of code that you use to do a calculation. But you need to put something there. Otherwise, it's extremely difficult for me to assign you any partial credit if you got a problem wrong. So please make sure you do show your work. Test is closed book, closed note, but you do have access to any of my R programs that are on my course website. So hopefully by this stage you're very familiar with the R programs for this section of the course. So if I ask you to estimate a Poisson rate regression model, you know to go to my horseshoe crabs program, and you have a general idea where to find that information about how to estimate those models. Or maybe you just know it off the top of your head, the code. Either way. But you need to have some familiarity. I strongly recommend having a lot of familiarity with my programs. Of course, you cannot look at my lecture notes. You cannot look at past answer keys. You cannot look at homework that's on my website. Actually, I will be taking those down before the exam so that you cannot have access to them. Of course, too, remember I can see what's on your computer screen. These are all set up so that I can see exactly what's going on in the classroom. Okay, are there any questions about the structure of the exam before we do a review of some of the material? Okay, so let's review here. So starting with Chapter 2, just a continuation of what we did with the binary regression models. The first thing that we started looking at was the interactions and transformations involving explanatory variables. How do we include that kind of information? How do we include those kinds of terms in a model? Also with these then, dealing with odds ratios becomes more difficult. So a very common question I've asked on the test before is maybe I give you a model with a quadratic term in it. Derive the odds ratio. Interpret it. Then we started talking about categorical explanatory variables. How does R represent categorical explanatory variables? How can you then look at odds ratios corresponding to these categorical explanatory variables? Again, I can ask you to derive a particular odds ratio. Make sure you're familiar with the factor function, the relevel function, and the levels function. What about interactions? So if I have a categorical explanatory variable, and I want to look at an interaction between that and a continuous explanatory variable, how would I do it? And what will be the terms that will be contributed to your model? Hypothesis tests, that's another thing that you can look at too. Of course, we look at all the terms corresponding to a categorical explanatory variable rather than one at a time. Then we started talking about convergence. Now, generally speaking, we don't have problems with convergence, but a problem can occur. What should be the first thing that you do? Well, find a large number of iterations. What would you look for if perhaps R said convergence did occur, but maybe it didn't? We looked at some examples of what to look at. Also, a big thing that comes up with convergence or convergence issues is complete separation. A very simple short answer question is, well, what is complete separation? What problems does it cause? Why does it cause it? Then we generalize these kinds of models, and we looked at generalize linear models. That allowed us to now talk about a probate regression model and a complementary log-log regression model. A simple question that I could ask you for a short answer would be, tell me what are the 3 components of a generalized linear model and what do they do? How does the probate model fit into that generalized linear model family versus logistic regression? What's the difference? What's used for link functions? And also, why are logistic regression models used more often than a probate regression model or a complementary log-log model? It all has to do with odds ratios. Okay. So then that got us into chapter 3. We started talking about multi-category, can't spell today, multi-category regression models. Well, we'll just say a multi-category response. And we started off with, well, what distribution is used in this situation? Well, it's a multinomial. Make sure you're familiar with the multinomial. You write a likelihood function associated with a multinomial. And you understand the different ways to think about how counts in a contingency table come about with respect to a multinomial. That then got us into testing for independence. So we looked at a Pearson chi-square test and also a likelihood ratio test, a test for independence in a contingency table setting. And make sure you can carry those out. We looked at using a chi-square distributional approximation to make a judgment, but we also talked about a Monte Carlo simulation approach as well. Then we started talking about regression models, and we first started talking about a multinomial regression model. You'll know the basics of being able to state the model, being able to estimate the model with the multinom function. Make sure you can estimate what pi sub j would be, so the probability of having a response in category j. Make sure you can derive the expression for pi sub j. I've given that on test before. Odds ratios come into play with these kinds of models too. You make sure that you can find odds ratios. And also working with contingency tables too. The next kind of model that we looked at for multi-category responses was a proportional odds model.
Sorry.
Yep.
When you said make sure you can estimate pi sub j, you mean in R?
Yep. So like use the predict function. But again, definitely make sure you understand how the expression for pi sub j comes about. So a proportional odds regression model. Now this is used, when you have a multi-category response that's ordered in some way. Make sure you know the basics of, can you write out the model? Why does it make sense to have a model like this when you have an ordinal response? When you look at those cumulative probabilities, it has to do with that. Why, also make sure you understand, this will be a good short answer question, why is this called a proportional odds model? Where does that name come from? Talked about that in class. Let's see now. So with this kind of model then, well, can you derive pi sub j? Can you estimate it also using the predict function in order? The main function that we used to estimate these kinds of models was called POLR. Make sure you're familiar with how to use it. Odds ratios come into play once again. and also contingency tables. And we looked at, what the advantages of using a proportional odds regression model are when you have an ordinal response. We focused specifically on the fiber data example. You remember that p-value that we got for our likelihood ratio test was a lot smaller with the proportional odds model than what it was with the multinomial model, which does not take into account any kind of ordinality. And so we saw the advantages of using the proportional odds model when in particular situations. And lastly, we also looked at a non-proportional odds model. Why is it called non-proportional odds? We also talked about what are potential disadvantages of this model. Make sure you're familiar with that. So lastly, then, that takes us to chapter 4, where we have a count response. So, know the basics of working with the Poisson distribution. Understand, when we like to find a maximum likelihood estimate. What is it for mu? And we spent some time talking about confidence intervals for mu. Let's see, the walled interval for the log of mu, which then transform back to mu, and the score interval. Which ones are better? How can you evaluate which ones are better? Then we got into Poisson regression models. Make sure you can estimate them. It's not too difficult. Use the GLM function. Make sure, again, you can use like the predict function with it. Make sure you understand Poisson regression's place in terms of the family of generalized linear models. So kind of the corresponding thing to odds ratios that we saw with logist regression is this percentage change, or what I call PC. Make sure that you can find the PC, derive it for particular situations, estimate it as well. Contingency tables also can come into play with respect to Poisson regression models too. And remember, we use the term people often use the term log linear models with these kinds of, in this kind of a setting. But there's a simple equivalence between a log linear model and a regular old Poisson regression model. Make sure you're familiar with it. And then lastly, we talked about Poisson rate regression models. Make sure you're familiar with the term of or understand what an offset is, or why we need to mix this particular kind of adjustment that we do with the Poisson rate regression model with the t value. How do we estimate the model in GLM? How would we calculate a PC, for example, with this kind of a model? Okay, so that's all I have specifically to say about the exam. Do you guys have questions? Yep.
Can we try your 2012 exam? Can we ask you questions about it?
Yeah.
We can't get something.
You can. Just, yeah. If you ask a question, don't ask the question, how do you do this? It has to be a directed question. Well, okay, I guess there's no questions. No, yeah, as I said, and I like to repeat myself sometimes, but sometimes I think it's important to. You know, I don't think this test is going to be hard. There shouldn't be surprises, as long as you study enough. Okay. If you have any questions before our exam, in addition to talking about the previous tests, please feel free to post to the listserv or stop by my office. So I guess we'll just end it early here today. So that's it.